Will I what? Bring it on Thursday? Oh, on Wednesday, yes. It wasn't there yet? Okay. Okay, so first of all, I'd be happy to answer any homework questions, and then we'll go on to an example that I want to do sort of two similar problems just to try to clarify one thing. Yeah? Mhm. No, in dynamics, we started centroids. In this class, we're just starting centroids. It's confusing for you and for me. Okay. Yes. Hey, what happened? What's wrong with the stupid thing? No screen. No screen. Can you guys see that? All right. Well, yeah. Well, that's good at least. Let's trash this place. um, okay, so yeah, let's do homework questions first. Yes. Okay, yeah. And that's on rigid body kinetics? Rigid body kinetics. Okay, 12 and 15. Yes. So is this going to work okay for you? I'd like to do it on here if possible, because at least then it would be clear on the, you can go to the PDF later or go to the video. But I also could do it on a whiteboard marker, so let me know. But okay, number 12. So you have this ball and socket joint at the wall. That connects to a thing with a circular cross section. And then at the midpoint, there's sort of like a sleeve that can slide. And then that long thing continues to the end. It has a round cross section, so there's the end. And this sleeve in the middle, there's a downward force F. And then there's a cable that connects to the end that actually, instead of going to the wall or something, goes to a pulley. And then one cable, goes over the pulley. One end goes to the wall over there. One end goes to the wall over here. I'm going to move this down a little. Dang it. Okay. And Now let's start figuring out some distances. So our axes are, so that and that and that. Those three are perpendicular to each other. This is the y-axis. This is the positive x-axis. And this is the z-axis. And let's see, we're going to go out uh, 4 feet to the side, and then I guess that's 5 feet up. Okay, so this distance here is 4 feet. This is supposed to go, well, let's see. It's supposed to be where this connects to the wall. So like this connects to the wall. It's 4 feet over. 5 feet up. You following that so far? Forget you then. Just draw it for myself. And on the other side, it goes out, oh, well, it's just straight across. So keeps going out this way. And it goes out to there. And this distance is also 4 feet. Anyone have any questions about what's happening yet? So both of these are, oh God, that makes it way worse. So each of these two attachment points are 4 feet out along the x-axis from that center point, and they're both 5 feet up along the z-axis. Oh. Yeah, I guess that was just for those. I didn't know there were two. Okay. And then this distance is 5 feet. And this distance is 5 feet. Okay, so that's about it. And we're going to name some of these points. I'll call this one A, and that's going to be our origin. This one B. This one C. This one D. The pulley is E. Okay. And I guess that should do it. I mean, I guess we can call this one F where that force F is applied. Makes sense. And just as an aside, when you're trying to draw pictures like this, you gotta make sure it's a little shaky or whatever, but really the idea is to pull how to make it look sort of nice and 3D just the x-axis, the y-axis, and the z-axis all have to be in, so choose the direction for those, okay? And it's not going to be at right angles if you're drawing it out, like skewed like this. Once you've chosen those, you just have to think of every line that you draw as being parallel to one of those three, you know? I mean, sometimes there are ones that aren't parallel to any of those three, but usually most of what you're drawing is parallel to those. And whatever's parallel to those needs to be parallel to that axis. So like this dotted line here is parallel to the x-axis, same with this one. And so they should look like that on there. And if you do that, it'll look okay, even though like I got too much copy today, I guess. But still, you can sort of, this isn't my best work ever, but you can still sort of see roughly what's supposed to be parallel and perpendicular. Okay, well, like we did with our last three-dimensional problem, let's come up with the coordinates of each one of these points. So the point A is at the origin. The point B, so how do you get to B? Start at the origin and go 10 feet in the positive y direction and you're there. So this is 0, 10, 0. The point C, to get there from the origin, you go negative 4 feet in the x direction, 0 in the y direction, and positive 5 in the z direction. And D is the same, except it just has a positive 4 in the x. Oh, and I didn't give one. You couldn't do it with what I gave you here. You also need to know this. This distance along the y-axis is 2 feet, yeah. That's true, but if you look at it from the side, it would do this. So if you look at it from the side, and then those points C and D would look like the same point. Okay, so, and they would each be 5 feet up. Okay, so I'll draw this as D. Okay, and it would be a straight line from here here. Okay, and so you can figure out the height from this triangle. You know this is, so you know this is 2, and this big one is 10, and this big one is 5, you know. And so that means that, you know, x over 2 is 5 over 10. So that height has to be 1. Okay. So that point E, it's going to be 0 for x. It's right along the x-axis. For y, it's going to be, you know, 10 minus 1, 10 minus 2, sorry. 8. And then for Z, it's going to be 1. Here's our coordinate system. This is Y. This is Z. Okay, are you with me on that one? And then the last thing we need is F. That's the last thing we need. No, we do need it. So that is 5 feet in the positive Y direction, 0, 5, 0. Okay, so now we got all those points. Any questions about that? Definitely the trickiest one is figuring out where that pulley is. But I think it makes pretty intuitive sense if you think of it, like picture what would happen from the side. We're assuming that that pulley, you know, has no weight. Cables and pulleys, we assume, has no mass, so it's not going to sink at all. All right, now that we have those, we can start to, well, let's draw a free body diagram. And then we can draw out the table. Okay, so what are the loads? There's this force F. Acting straight down. There's no weight force. We're assuming it doesn't have any mass, or that the mass is negligible compared to these other forces. It's a ball and socket joint at the wall. And so what kind of loads are applied by a ball and socket joint? XYZ forces. Yep, there's no translation of that point allowed, but it can rotate about any axis. So we have a force vector with components that way, and that way. We'll call that RA. Okay. And then, okay, now I want to be a little careful. Now we could do this by the base of the body nicely. And then the only other force, have I got everything on it? Yeah, so the only other, so we dealt with the weight, which was ignored. And then we apply this force to the boundary. This force to the boundary. The only other place the surroundings makes contact with the boundary is this little cable touching the end. But I think for what it asks for, it asks for the tension of this cable, not the, let's see, does it say? Calculate the reactions. Well, I guess that means we would want to know I guess we'd want to know that means we want to know the tension in this big cable and the tension in this little cable. How are we going to do that? I think we're going to maybe have to do it in 2 steps if we want both of those. So maybe for now, let's just do it like this. And then we'll go back and figure out how to get the tension in that big cable. So if this is the free body, and we're not including the pulley in our free body, that's external, then the only other force that's applied is a force this direction. And I'll call that one just T, okay? So that is the force vector applied to the point B, you know, to this long member by that little piece of cable before you get to the pulley, okay? Then once we get that, we can isolate the pulley and we'll be able to figure out the tension in the other one. The other thing you could do if you didn't want to figure out the force in this cable, this little short one, you can isolate, so include in the body you're isolating that little cable and the pulley here. Then the force is applied to our chosen body by So you kind of have a choice in that, but if you want all of those tensions, you're going to need to do it in 2 steps, no matter which way. Yep.
So you can have like the small cable do like one tension. So essentially,
So,
three variables you can make there.
um,
You wanted to isolate all of them.
if you wanted to isolate all of them, what you would isolate is like your free body would look like this. You'd have this long thing, and then you'd have this, and it's all part of your body, you know. And so then you have a force here. Well, it's the same cable, just going, so they're both, you know, call it TA or whatever. So you have the force here, and then you have this force T2 maybe, and T2 over here because it's the same cable. And now that force that's applied to the body by that short cable doesn't show up anywhere because those are internal loads. Okay? That's a load applied to the body you're isolating from the body you're isolating. It doesn't show up. So this just lets you figure out which one of those two you want to calculate. Let's do this one. All right, so now let's draw out this table. So rho, force, moment. And for the about point, let's put it where that ball and socket joint is. And one of the nice things about that, since that's the origin of our coordinate system, is the rho vector is just going to be the coordinates where the force is applied, and we already have all those coordinates. So for RA, the rho vector is 0. The force vector is RAX, RAY, RAZ. And the moment cross 0 with that force vector, you get a 0 vector. And next, let's do that force F. Now this one is a little different than other problems we've done because this external load, it's not like we can calculate what that F is. That's a parameter that everything else is going to depend on. Okay, like if that force F was 0, there'd be no forces in any of this other stuff. Okay, so F is just something we're going to have to include in our answers. Most of your calculators will let you treat a variable like this as a constant in reduced row echelon form. Some of yours won't, and then you have to come up with another way around. In this case, the way around is probably just doing it by substitution instead. It's not going to be a complicated. Okay, so that force F is in, it's in the negative z direction, and it's applied at the point 0, 5, 0. Okay, so the rho vector is 0, 5, 0. The force vector is 0, 0, negative F. And so the cross product is negative 5F, 0, 0. And then the last thing we need is that cable force T. Well, the rho vector where that's applied, that one's pretty easy. That's applied at the point B, so 0, 10, 0. But to figure out the direction, well, we can think of it, there's a couple ways we can think about it. This one happens to be in a plane, right? This is, that cable from B to E lies in the YZ plane. You see that? So we could do it using cosine and sine in the YZ plane. For 3D problems generally, you know, I always say, like in 3D problems, don't even try to think of cosine and sine. Just find the beginning point and the end point and subtract and then normalize it. So let's do it that way. So the vector we want goes from B to E, okay? So a vector in the right direction is E minus B. So that's 0, 8, 1 minus 0, 10, 0. And so you get 0, negative 2, 1. Does that look like about the right direction for the vector we want? Yeah. Negative y direction, positive z direction. Okay. But that's not a unit vector, and we need it to be a unit vector in order to multiply it by t and get a vector that has a length of t. So the unit vector is 0 divided by root 5, negative 2 divided by root 5, 1 divided by root 5. And do I know that? I think, no, what is that? Okay, 0, negative 0.894, half of that, 0.445, 0.447. Okay, so that's a unit vector in the direction we want. Now multiply that by the variable t, and you get this force vector 0, negative 0.894 t, positive 0.447 t. And the cross product of those two is 4.47 t 0, 0. So now Newton's second law, we'll just add up all those forces in the force column. So we got RA plus 0, 0, negative F plus 0, negative 0.894 t, positive 0.447 t, is equal to zeros. And the moment equation says 0, 0, 0 plus negative 5F 0, 0 plus 4.47 T 0, 0 is equal to zeros. Two of these moment equations don't give us anything, so forget about the y component of that equation and the z component of that equation. Okay, so we got 6 useful equations. How many variables? Now, because we know we can't solve for more than 4 variables. 1, 2, 3. T is 4. F looks like 5, but remember, F isn't a variable. That's the parameter that drives this equation. What we're basically doing is like your boss says, we know we're going to apply this force F, but the engine people haven't gotten back to us yet on how big that force is going to be. You know what I mean? So just leave that in there as F and we'll plug it in for F later. Okay. All right, so what can we calculate? Okay, well, we know that so we have equations 1, 2, 3, and 4. Equation 4 tells us that negative 5f, so let's say, what comes up more? Let's say t is equal to 5 divided by 4.47 f. What's 5 divided by 4.47? 1.119 f. Okay, and now we can plug that in to the other equations. So plug that into, let's see, plug that into 2, and we get that RAY is equal to 0.894 times 1.119 f. So what do you get for that? Just f. Okay. So RAY is equal to f. And RAZ is f minus f minus 0.447 t. So that is f minus 0.447 f, so that's 0.553 f. Okay, so we got t in terms of f, and the RA vector is 0 for x, f for y, and 0.553 f for z. Any questions about that? Okay, so now we already calculated all the forces that are applied to the, that long member. But what if we wanted to calculate the tension in that cable that goes from D to E to C? Okay, then what you do is isolate that pulley. Try that again. Okay. And what you have is force this way applied to that pulley, what's the magnitude of that force? That's T, yep. So, and we know what T is, so that's 1.119 F. And now we have another cable force that goes this direction. I'll call this T2. And this direction, that's also T2 because that's the same pulley. We're treating the pulley like a particle that just exists at the center of the pulley. So now it's just a matter of Newton's second law. And I guess one of those two equations hopefully will be enough because we only have one variable. All right, so Newton's second law. So we know we have this force vector, this one. We can just plug in the value for t. So it's 0. Those are switched, I guess. All right, so if there was a way to think of this in another plane that would simplify the geometry, that'd be sort of nice. But I guess we can go, so we know that the magnitude is this, right? And we know that, so forget about this. This is a ways off still. So let's deal first with that single cable. So first we'll do the one that has a magnitude of 1.119 F. Okay. We know the direction is, well, we know it goes from E to B, okay, which is the negative of the one we already have from B to E. So that's, so our unit vector is the opposite of the other unit vector that we already came up with. So it's going to be 0, positive 0.894, negative 0.447. Okay, and that tells us that the force vector is this times the magnitude of that cable tension, which is, so we have 1.119 F times this unit vector. And I think that might just be 0 F, negative half F. Okay, so that's the first one. We have to do the other two now. So now let's do the cable that goes from the pulley to D, okay? So from E to D. Well, a vector that's in the right direction but not a unit vector yet is going to be D minus E. So that's 405 minus 081. So that's 4 -8, 4. Question? Let's see. So we're trying to figure out the force. We're trying to figure out the force that that cable applies to the pulley because we're isolating the pulley. So we want a force that starts at E and goes to B. So that's going to be B minus E. So I think I have it right this time. Okay, and then if you normalize that, you get a unit vector. I think it's 0.408 -0.816 +0.408. And so the force vector is this times that tension T2. So this is 0.408 T2 -0.816 T2 +0.408 T2. And then the third one, the cable that goes from E to C, the only thing that's going to change there is the X component is going to be negative. So we're going to get -0.408 -0.816 +0.408. And so now we can go Newton's second law. We have to add up those three force vectors and set them equal to 0. So we have 0F -0.5F plus 0.408 T2 -0.816 T2 +0.408 T2 plus -0.408 T2 -0.816 T2 +0.408 T2. Set those equal to 0. And this equation, you know, those two non-zero terms cancel out, so that totally goes away. And then the other two are multiples of each other. And so really that's just a single equation. You can use either one of those to find the value of T2. So let's use F is equal to 1.632 T2. And so what do you get for that tension T2? What's 0.613 F? So we did figure out that you need a lot stronger. So if you're figuring out, you know, trying to figure out where you have to use your expensive cable not quite twice as strong, but. Any questions about that one? Okay, and then the other question was 15. Okay, so this one, you have a pin joint over here. And that connects to a big gear. I'm just going to draw it like a disc. And then it gets to a second pin. And then that rod extends through the second pin and gets to a second smaller gear. I'm just going to draw it like a disc again. Okay, so you got to set up like that. Each of these is connected to the ground. And there are loads applied to the big disc. There's a downward load of 96 pounds and a horizontal load this way of 265 pounds. And then on this disc, there's a horizontal force of 192 pounds and an upward force of 530. And the dimensions we have 4 inches here. Three inches here, doesn't look like it, and 2 inches here. And we want to calculate those reaction forces, reaction loads. I wanted to do an example like this today. We're calling this the z-axis, and this the y-axis. And then the x-axis goes this way down the rod. So what we're going to isolate is the rod and the gears. And we have those two pin joints acting on it, you know, the loads from these 2 pin joints. And pin joints are the complicated ones in 3D. So remember, they can apply couples, but they don't always. And so anytime you see a pin joint, you have to ask yourself, am I applying those couples or not in this case? In this case, it's 2 pin joints working together with the same axis so instead of this one, like, imagine this one isn't here, okay? Then this could apply any couple you need. If I pull this way, or, well, you can't apply the twisting one, okay? It would hold it in place if I pulled this way or pulled this way, up to a point, but eventually it would just rip this off of its bearings, you know? Same with if this was the only one and not this one. It would be able to apply those couples up to a point, but it doesn't do it very well. And so if you have two of them sharing the same axis, the idea is they don't have to apply those couples that they don't do very well. They each have sort of each other's back. Like if I tried to pull this, okay, instead of this having to apply a couple, it just applies a force this way. That one applies a force that way, and that gives the couple instead of the joint itself doing it. They can apply combinations of forces rather than their own couples. And so in this case, we're going to treat each one like it only applies forces. Okay, so the pin joints are coaxial. So they don't apply couples. Okay, so let's draw the free body diagram now. So we have the rod, the big gear, the small gear. Okay. We haven't talked at all about whether these joints apply thrust or not. Usually you have to know that. You have to know, and usually one of those joints, those coaxial pin joints, will apply thrust and one won't. In this case, since there are no external forces that would make it move along the z-axis, it doesn't matter. Neither is going to have to apply a force anyways. Do you see that? So if I applied, if there was a, so there are external forces applied up here and over here, okay? And if there was another external force like this along the axis, then I have to know which one of these two pin joints is going to keep this from shooting out through the bearings. Okay? You follow what I'm talking about? But since there's nothing doing that or going the other way, it doesn't matter. There's not going to have to be any force horizontally to keep it in place. So normally you have to know, like, you look at something like this and you want to know which one of these is going to apply the thrust to keep it in place along the axis. The only time you don't need that is when there's no other force that's tending to push it through the bearings. All right, so we have a force vector here. It has a component like this and a component like this. Okay, what are we calling those? The y and z direction. So we have a force vector. Let's call this RAY and RAZ. And then we have those known external forces applied here. That's a downward force of 96 and a horizontal force of 265. And then we have the forces at the other bearing. So let's call that RBY and RBZ. And then we have these forces. Horizontal force of 192. Upward force of 530. Yep.
On the problem, it gave the radius of the disk. Is that needed?
Yeah, that is needed because that determines where those forces are applied. Okay, because like if this radius was an inch, then these forces would be applied up from the axis. You know, if it's a mile, then they're going to be applied a mile, and that does have an effect on how big the moment is. Yeah, so let's see what we can. So our origin is going to be here, and let's also make that the about point. And now we can write out the table. Rho, force, moment. For that force RA, the rho vector is 0. The force vector has no x component, but it has a y and a z. And cross product gives you 0 for a moment. And then the forces on the, I'm going to just call this big, on the big disk. So the rho vector, so the vector from the about point to where that force is applied. So we have to go 4 inches in the positive x direction, and then the radius of that disk, 0.5 inches in the positive y direction. $1.5, yes, thank you. Okay, so 4x, 1.5y, 0z. And then the force vector, so we have a, let's see, we have a y component of negative 96, a z component of positive 265. Can someone take that cross product for me? Okay. $10.16? 1060. Okay. Negative 384. Okay. Yes, it should be negative. What? Oh yeah, first one. That could be. First one's positive, second one is negative. Okay, so that could be right. That looks right. Okay, and now we get to the force RB. The rho vector there is, so it's all in the x direction, 4 plus 3, so 700. The force vector is 0, RBY, RBZ. And the cross product is 0 for x. And then negative 7 RBZ. and then positive 7 RBY. And then the last one is on the little disk. The row vector to that point, that's on the front of that little disk, is, so to get there, you have to go from the about point 4 plus 3 plus 2, so 9 inches in the positive x direction. And then you have to go 1 radius, the little disk, in the positive z direction. So 9, 0, positive 0.5. And the force vector in the y direction is positive 530, 0 for x, 530 for y. And then for z, it's negative 192. Can someone cross those two? $1065 negative 265. Okay. Okay, sorry. What's y? 1728. Okay. Okay. All right, so now let's see what we have. Positive, okay. All right, so what do we have? Well, first let's figure out how many variables we have. 1, 2, 3, 4. 4 variables. So we need 4 equations. You can see that the x force equation is going to disappear. So we're already down to 5 equations. And then, if you think about the way this is going to work, there's nothing to keep this from spinning about the x-axis, right? Follow that. And those forces, so if those forces don't add up to a 0 moment, you know, the couple from this, the moment from this, and the moment from this don't add up to 0, then this thing's just going to spin. But that doesn't change any reactions. Okay? And so the second equation that we don't care about is the x moment equation, the one relating to rotation about the x-axis. So even though this one doesn't add up to 0, we don't care about that one. And that gives us 4 equations for 4 variables. Any more questions about that one? Yeah. So we're just trying to calculate reactions, and none of those reactions relate to slowing down that rotation. Okay. If one of these was a fixed joint or something, then yeah, like there would be something fighting the rotations that's produced by those forces. But if you just think about how this setup would work, I mean, so the first thing is like mathematically looking at it, there just aren't any reactions that relate to that. There aren't any variables to calculate in the x moment equation. So if there's no variables involved in the x moment equation, it doesn't do any good. But then just looking at it physically, thinking about it intuitively, you can see that, I mean, if you apply, like, if you do something to make these things rotate, and the setup is like this, where you just have a pin going here and pin there, the thing's just going to spin. And that's not going to affect how much force is applied here Any other questions? Okay, well, that was actually a pretty good pair of problems for today. I think maybe I will do one example on Thursday, and then we'll get on to centroids after that. Okay, that's all. Okay, leave. No.
I have one more question. It has to do with like what core it has to do with what we're talking about. So number 10, it has 2 points. Is it highlight the same thing? Almost like
Yeah, you know what I would do on that one? They're the same magnitude, but you need those forces to be in there. So what I would do is keep that cable in there. And then your external loads are just the cable coming out there, the cable coming out there. They each have the same magnitude. Okay. And then you can use that. You'll be able to calculate that T, and that'll let you calculate it.
So essentially my three-letter diagram is then the final thing.
Yes.
So essentially we're just be like this, and I would have to find this or what these values are, this value, and then this T value. I wouldn't have to like find this one.
That's right, because that's all internal. Okay. Yeah, exactly. Okay. Okay, thank you. Sure.
I have a question about the we just talked about on the 12.
Yeah.
You see there's the second one. You see this one just opposite with that one, opposite direction. I think because when I'm looking the picture, it should be the 1 point down here. There's 2 over there. I don't think this one is the opposite direction.
Well, they give the like looking at it front on. We didn't look at it from this view, but it was like the pulley was here. This one went here, and this one went out here. And these are symmetrical. Yes. You know, it's the same distance that way and that way. Yeah. Yeah, well, it wasn't exactly the opposite. It was just one component that was opposite. So this, the unit vector for this one was like, so for x, it was positive 0.894 or something, and then negative 0.447. I guess y must have been the big one. So 0.447, negative 0.894, and then positive 0.447. And then this one, the only thing that switched was the x component, negative 0.447, negative 0.894, positive 0.447. And that's just because, so instead of going this way, positive x direction, it does the same thing in the other direction, the negative x direction. Sure. someone from the just from. Okay, great, thank you.
Hi. So this is origin, right? Here's
Yeah.
origin. So if this is origin, so this is line of action, right?
Mhm.
So why you calculate this height? Since this is line of action, we don't need this height.
Yeah, so, so you're right that you don't need that. Well, actually, you do need it, no matter what. Because, you have to know, so if you look at it from the side, okay, it goes like this, and then there's the pulley, and then the pulley goes, keeps in that same line. That should be straight. Even though that's two cables, but they sort of overlap each other. And you need to know how high it goes so that you know the direction of the force that this cable is applying to this. And then so you know the direction this cable is applying to the pulley later. Because otherwise, like, you could, if you didn't know that height, it could just be straight back or something, you know. And if it's straight back, it's going to actually require a much bigger force than the angle it's at. This idea? Okay. You don't ever need it, but sometimes it lets you just eliminate some values that just make the math a little more complicated. But you never need to do it. Okay. But in this case, you know, the line of action is this. So, yeah, you could say that that force is acting anywhere you want it along here, but that's sort of a tedious line to deal with. It doesn't really help you to move it along this line. You know what I mean? Like, think about what a pain it would be just to figure out where a point is along that line, you know. Okay, sure. Hi.
You get my email?
I don't know if I got your last one, but there's a test in the test.
All right, perfect.
And it's there, I think Friday.
All right, perfect. Yeah.
Okay. Sorry about that. Yes.
Yeah, no problem.